Hi, this is Guanlin. I'm working alongside Xingze, Michael, and Jerry. Our project is GEMMASTER, accelerating NLP models through GEM quantization on FPGAs. So we try to figure out an efficient way of accelerating attention layers and activation layers of transformer-based NLP models by applying different low-precision data formats on the HS tool. NLP model become very trending recently. After the release of ChatGPT 3.5, more and more LLM emerged recently. However, most of them face challenges like the computational intensity increases in a crazy way, and it's also the same to the utilization. Transformer-based NLP model demands substantial computational power because of the super large amount of parameters. And it also requires longer processing time. So these factors are gradually being the bottleneck of this field. So half of the power consumption of NLP models comes from mathematics-related operation, like the data movement between memory and onboard chip, and also the operation like multiplication of two data. Low-precision data type reduces the power consumption significantly. It could also reduce the usage of memory space. Like the memory space used for 132-bit data can also be used for 8 inferred data. So in this way, it could get us a higher memory throughput. What's more, a low precision data type requires fewer cycles for the multiplication, which means it could improve the performance of the model in latency-wise. So for this project, the listed data type here are the popular choices of the low precision data formats. I think most of you are familiar with some of that, but it's not the same to the NF4 and E2M2. And NF4 is like we're building a lookup table and build a relationship between the original matrix to the NF4 values. And for E2M2 is popular in Catapult HS, but so it's like a customized basic flow data type, which you have to limit the bandwidth of the matriza and the exponent.
Hi everyone, I'm Xingze. I will introduce you the attention layer and our concern about the hardware usage and show you some results. So about the attention layer, generally there are 3 inputs, matrix Q, K, V. We multiply matrix Q and K, we get the result and scaled, and we send it as the input of the softmax module, and we do the softmax for each row, and we multiply the output with the matrix weight, and we will finally get the result of the attention layer. That is how attention layer works. So about the hardware ecosystem, the reason why people design storage and computation-efficient data types results from the limited hardware resources. In terms of deep learning models, if someone tries to do inference on FPGA, the memory space of the board can only store 10 models. For example, our FPGA board can only support 5 megabytes on board memory space. So on the other hand, the customized data type significantly reduces the resource usage like DRAM with less bandwidth while keeping the accuracy of a computation module. You can refer to the table aside to look how the bandwidth of the data decrease and the DRAM usage also decrease. So I have mentioned the resource usage in previous slide. We should focus on the accuracy difference. So here we can see that as the bandwidth of the input data increase, so the accuracy also increase. However, there is a knowledge that when we restricted the output bandwidth, the accuracy increase, however. So it doesn't matter because all of the errors value are too large, so we can eliminate this.
Hi, I'm Michael. So I'm going to talk a little bit about some of the actual implementation of some of the code that we use for our attention mechanism. So for our attention mechanism, there are basically 2 different aspects that we sort of need to focus on. First is the data that we're going to use for the attention mechanism, and the second is the actual aspect of doing the attention mechanism. So for the first part, the data generation, basically what we did for the data generation part, aside from instead of using an actual data set, we basically just took a normal distribution that we generated in Python of random data, and we forced that random data into this random distribution. And this on its own would be fine if we just wanted to test the attention mechanism, but because we also want to test different data types, we decided that it would make more sense to do the quantization of the data types offline and then use the offline computed quantized data on the FPGA afterwards, so that we're not adding additional compute on the FPGA to do the quantization process. So basically what you see here in this example code is basically that we have this two sets of matrices that have random sets of data generated for them that's been forced into this normal distribution, and we take that data and we're going to force it into a data type. In this case, we're going to use the int data type, and we're going to cast that data type, and then we'll use that output data as our quantized data for the input matrices. And if that doesn't make sense, here's a quick example to show you the general flow of how we're approaching this. So the two matrices on the right basically represent the original values of what an attentional mechanism would typically use as its input matrices for the query matrix and the key matrix. But since we want to do quantization, basically what we've done is we've taken this data and we first quantized it to, for example, in this case, the int type. And basically what we've done in this type is just cut off the decimal bits and used only the integer bits. Now that we have these two quantized integer matrices, we'll take those two integer matrices and we'll do the matrix multiplication of that to get the output of the gem. And from there, we'll do some scaling to make sure that our softmax doesn't get too exponentially out of hand. And in this case, scaling doesn't do too much because the values that we have are so small to begin with, it doesn't really impact it super much. But with larger matrices, the scaling would have a bigger role. And after that, we'll do basically row-wise softmax on each of the rows of the output matrices. We'll do a softmax on it, and that will be the output of our attention mechanism. So going into the actual attention mechanism itself, basically what we have is three aspects. We do gem, which is the simple matrix multiplication, and for this, fairly simple in C, we just have two matrices, we multiply them together, and we store that output in an output matrix. The scaling is fairly similar. We'll use a matrix multiplication basically, but with a constant instead. The softmax is a little bit trickier because we're using an FPGA, we want all of the code to be synthesizable. So we can't use things like the math library in C++ to implement our softmax. So basically what we've done is we've used the Taylor series to implement the exponential function, and this gives us a fairly accurate estimate of what our softmax would traditionally give us. There are a few issues, however, with using this Taylor series estimation. One of the main issues is that because it's only an estimation and because the values that we're working with are super small, any difference that we have between our actual input and the estimate that we have is going to become scaled up once we do the exponent with it. So our data quickly becomes disproportionate with our gold standard data. Another issue that we had is that when we're using different types of data types, sending that different data types to the FPGA is difficult and it's often inefficient, and this is something that we should be able to improve upon in the future. So I won't be showing you a demo just because doing the actual attention mechanism on the board is quite time consuming. So this is something that we could potentially look into a little bit into the future if we wanted to explore this a little bit further. Basically, two 4x4 input matrices with the N4 quantization is extremely, extremely slow. It takes 6.5 minutes to do it. And with the N4 quantization, because we're using the Taylor series estimate and not the actual value, you can see here on the right that a lot of the Python output, which is our gold standard output, and the calculated output from our attention mechanism calculation, there is quite a bit of difference depending on how large the value gets. And this accuracy is something that needs to be looked into if you want to consider this, I guess, on an FPGA. And I guess Jerry will talk a little bit more on some of the work that we could potentially do in the future to mitigate these issues.
Hi, this is Jerry. I'll talk about some of the future works that we can do. For example, we could explore a higher accuracy implementation of the softmax to reduce error. We're currently using the Taylor series to approximate the exponential function, so there's always a difference between the actual result and the output from our implementation, especially for matrices with large numbers. Our solution right now is just to limit the numbers, but this is not realistic for real-life data sets. So for our further exploration, we could think about other approaches to implement softmax with a higher accuracy. This also leads to another area that we can look into, which is to use the real-life NLP dataset. Right now, we're just generating our data set randomly with normal distribution, but the data used in the NLP application may be drastically different. So being able to test our implementation on these real-life data would be really, really meaningful. Another area that we can improve on is to use adaptive quantization, where the NLP program can switch between precision levels based on input data characteristics, so we can achieve speed up when necessary and preserve precision when we need. Lastly, we can also use pragmas such as enroll and pipeline to exploit memory access patterns to further enhance performance. This is all of our presentation. Thank you for listening.